under influence of air resistance. Now, air resistance is quite different than surface friction. Surface friction, remember, when we were talking about kinetic friction, I said that the kinetic friction is independent of how fast you're going. It only depends on the normal force. But the air friction depends quite a bit on how fast you're going. The faster you go, the more air resistance there is. Okay, so let's imagine here an object starts out with an initial velocity 0, and we let it go. Initially, the only force on it is its weight, mg. So it begins to accelerate at an acceleration of g. By the time it falls a certain distance, it achieves a certain velocity already, and the air friction is now resisting it. The air friction is equal to negative BV. B is the coefficient of air friction. V is the velocity that the object is going at. So the air friction is linearly proportional to velocity. Now, it depends on the kinds of air friction. This is an approximation. Some depends on the situation, but some kinds of air friction also could depend on the square of the velocity. Or it could be either somewhere between linear and square. So it's not a hard and fast rule that all kinds of air friction are always linear. But we do know that it has some dependency on velocity. So in here, we're going to assume that it's a linear dependence. The faster you go, twice the air friction. Three times the faster you go, 3 times the air friction, like that. It's a linear dependence. So now what's going to happen? Because the air friction is resisting you, you're not going to accelerate as fast, right? So you're still accelerating. By the time you get here, the air friction now grows a little bit more. And then you still accelerate a little bit, but not that much. By the time you get here, you get to a certain situation where the air friction equals your weight, right? That's known as terminal velocity. When you have achieved such a velocity where the air friction opposes the weight, and then you're no longer accelerating, you have achieved terminal velocity. So when mg equals bv terminal, v terminal equals mg over b. Okay? So that's the fastest speed that the object will reach under the influence of air friction. After that, it's not going to accelerate anymore. So after that, A equals 0. Okay? Now, what is this constant B? This constant B, let me just mention that a little bit. F air equals negative BV. The constant B is some constant that describes how thick the air is, how dense the air is, and how much it resists you. The units of the constant B is newtons per whatever the units of velocity is, right? Meter per second. Our class is at 3:30, right? Yeah. You're half an hour early. Okay. Or in the British system, it would be pounds per feet per second. And B is a constant that depends on how dense the air is, right? B depends on the density of air. Oftentimes, the B is also given the name viscosity. If you drop an object like this, could be you're dropping an object in oil and it's falling in oil, right? The viscosity of the oil is a measure of the friction on the, the object that you drop there. So, so B depends on the density of the air, and it also depends on the surface area of what's falling. The smaller the surface area, the less friction, right? Okay, in a minute I'm going to illustrate this here. I'm going to drop a piece of paper, crumbled, and then I'm going to drop it flattened out, and you're going to see the flattened out takes a longer time to reach the ground, The air friction is going to be more. Okay, so now the next thing that we want to do is to come up for a set of equations that describe how the velocity changes as a function of time. Now this is known as a differential equation. And basically the way to set this up, I'm just going to show you how to set it up, then I'm going to give you the solution. You say mg minus bv equals to ma, right? And then the a is equal to dv dt, the derivative of the velocity. And then we cross multiply here, we get this equation. And then we integrate. Okay? The reason why we're doing this is we want to come up for an equation for the general equation for how the v changes as a function of t for an object that is undergoing free fall in the influence of air friction. So v as a function of t. So the final answer, when you're all done with this, this is what the answer comes out to be. Okay? Because when you integrate the mg minus bv, you get an ln, natural log, right? And then when you raise both sides to the power e, that's where the e comes from, right here, exponential function. Okay? And then when you take the derivative of this, it gives you the general function a as a function of t. The derivative of that here, the derivative of the exponential, the negative will come out, the b over m will come out, and you're going to end up with g e to the minus bt over m. Okay? And then when you integrate it, you're going to end up with the integral of 1 is t. The integral of this, it's going to come out as reciprocated. Minus m over b. Okay? It's going to come out like this. And when you take a look at my notes online, you will see that I have shown more step-by-step process of how this differential equation works out. Then I take the derivative. You'll see that a little bit more detail. So right now it's not that important to go over it all over again. So now I want to show you how to use this, okay, how to use these equations. So I'm going to take a piece of paper now,